So our next session will be J.C. Sandler, and with he will, as the session chair, he will lead to our junior faculties to talk about the future of physics, theoretical physics. And you have seen the videos, so none of them need introductions now. Okay.
Great. Well, thank you, everyone. So what you've learned about us thus far is that we're extraordinariuses here. You've learned that we are very good at nonchalantly walking from one office to another. And apparently we are the future of theoretical physics in the sense that all of us, I guess, here, we're joined by the fact that we've been at the CTP for, I guess, 15% of the CTP's existence or less. So I'm joined here by Will Detmold, Daniel Harlow, Tracy Slatcher, and Aram Harrow. And we're going to talk about something, hopefully, that will be exciting. And this whole event is a little bit like a family reunion where you get to meet long-lost parts of your family. And I guess this is kind of the children's table. And hopefully we can get a little bit of fun dialogue and not throw too much food at each other. So I guess I'll start with you, Will. Maybe we can just start with the present of theoretical physics. I mean, we were kind of thrown in this panel together just to save some time. So if we had another 2 hours for this symposium, what would you actually be telling us about this afternoon?
Right, so I'm Will Detmold, and I work on the strong interactions in particle and nuclear physics. So I do calculations that try and tell us about experiments at a whole range of energies, going from low-energy nuclear physics experiments to experiments at the LHC and searches for dark matter. And I kind of provide standard model input to those experiments and hopefully enable them to see something that we don't control in the standard model. I guess the things I'm excited about at the moment are, firstly, trying to, as a theoretical physicist, trying to understand what these calculations tell us, for example, about nuclear physics, not just in the context of the nuclear physics we can do in the lab, but what does nuclear physics mean more generally? For example, if we change the values of the quark masses or the number of colors of QCD, what happens to that theory? And then also, I'm interested in how we do these calculations. And so one thing I've been working on recently is trying to use machine learning techniques to make our QCD calculations go faster and faster.
Great. Daniel.
So I'm Daniel. Like I said in the video, I work on black holes and quantum gravity. So gravity, quantum mechanics has been around for a while. Gravity has been around for a while. Somehow, combining them is continuing to prove difficult. It's kind of puzzling. I mean, electromagnetism and quantum mechanics were combined almost immediately, and yet here we are, 80 years, almost 100 years later, and we still haven't combined really successfully quantum mechanics and gravity. And in some sense, black holes are really the reason for this. The problem with gravity is that everything is charged under gravity. There's nothing that's neutral under gravity, and that means you can have a region where the gravity is so strong that nothing can escape. If you had something that wasn't charged under gravity, you wouldn't have black holes, because whatever that thing it was, it could get out of the black hole. And this has led to this funny thing that somehow theories of quantum gravity are really very different from theories of the other forces, and they have this, in particular, this very surprising property that they seem to live in a lower number of space-time dimensions than the number of space-time dimensions that we see around us. So I don't know. At first, that seems very counterintuitive. Somehow, how is our space-time realized in terms of this microscopic theory in a lower number of dimensions? So and recently I've been using techniques from quantum information theory to study this problem. Like we said in the video, there's this interesting connection between quantum error correcting codes and where these extra dimensions come from mathematically. I've also been using ideas from quantum information theory to argue that there can't be global symmetries in theories of quantum gravity, which again is clearly something that is not true when you don't have gravity. So I don't know, fun things to think about.
Great. Tracy.
Okay, I'm Tracy Slatcher, and as you just heard in the video, I think about dark matter along with a chunk of the rest of the CTP. So I think about what dark matter could be, what properties it could have, how dark matter could be produced in the early universe. But my main focus is trying to understand how we might be able to constrain fundamental physics in general, but dark matter in particular, from astrophysical and cosmological data sets. As you saw, that involves some digging into astrophysical data. It involves thinking about the early universe. And if I was going to if I was giving a talk here, what I'd probably tell you about is what will hopefully be 2 papers appearing with my awesome grad students, which should be up on the archive Monday night if we succeed in finishing them this weekend, which are both dealing with, yeah, so the pressure is on my grad students in the audience. Which both deal with the possible signatures of dark matter interactions with the visible matter through annihilations or through decay or through scattering on the visible matter in the early universe, and how we can test these by measurements of what's called the end of the cosmic dark ages or the cosmic dawn. And this is especially part of the reason that we are trying to get this wrapped up this weekend is just a couple of weeks ago there was a claim of the first observations of a measure of the temperature of the universe at the end of the cosmic dark ages. And as you will find out if you read our paper on Monday, if that result was confirmed, you can actually say some quite strong things about the properties of dark matter. It takes us into an observational space that we have never been in before.
Great. Okay, Aaron.
So my name is Aaron Harrow. I work on quantum information, quantum computing, quantum algorithms, a field that is still theoretical, but I'm hoping we'll get the key to the cabinet where they keep the quantum computers, and soon it will move into an empirical phase. And if I were to give a talk, I would maybe talk about something I've been excited about recently. I guess, like many people, I've started thinking about machine learning. And the thing many people want to use machine learning, but I was thinking about how a quantum computer might contribute to it. In particular, in a sort of hybrid way, working with a large classical computer. Kind of one inspiration here is centaur chess, in which we know that computers can beat us in chess. But for a while, it's been true that a human plus computer team has a better chess rating than the best computer, although I think our edge is shrinking. So quantum computers are coming, but they will not fully displace classical computers. And how can they work well together? I have a few ideas for this, which I'm developing, and I'm kind of excited to explore this more in the future.
Great. And I guess I'll take this opportunity to answer my own question. So according to the video, apparently I only work on dark matter. But actually I also have interests in collider data analysis at the Large Hadron Collider and also in some formal aspects of supersymmetry. And it was great to take over, I'm not sure where Dan Friedman is, but take over 8831 from him and get a chance to teach that last year. And if I were giving a talk, I would tell you about the fact that there's 3 types of essentially data analysis problems that seem very different but actually share the same mathematical underpinning. Analyzing jets at the Large Hadron Collider, trying to get information about the CMB out from microwave data sets, and if someone just hands you a stack of documents and says, what are these documents about, having a computer figure out automatically what the topics of those documents are about, those actually turn out to be mathematically very similar problems, and you can actually use topic modeling of documents as a way to parse data at the LHC. And there's also another interesting connection between CMB data and the LHC in that in the case of the CMB picture itself is beautiful, but the actual information is in the power spectrum. And I'm one of those people that thinks that collision event displays are beautiful. But with my students, we figured out a way of kind of reprocessing collision event information and kind of the analog of the Fourier transform to try to find a basis where those signals of new physics might be easier to tease out. OK, so that was the easy part, talking about the present. And now for the rest of our time, we're going to be talking about the future. And 50 years is a long time. People have been talking about, CTP the next 50 years. And I don't know, 50 years, maybe I can imagine still being productive 25 years from now. And so I imagine that, I guess, Krishna, you were one of the organizers here, 25 years in the CTP. And I imagine that I am going to be one of the organizers for the CTP at 75th. And I want to get opinions from the panel about, what are we going to be doing in 25 years from now? What questions are going to be irrelevant? What questions are going to be central? What do we not know now that we will know then? What are trends that you see now that maybe if you tried to blindly extrapolate might teach us something? And here, I think for each of us, maybe, I'll give you 1 or 2 minutes before interrupting. And then we're just going to go at it. So I don't know. Will, do you want to start about this? What do you see us discussing at the CTP at 75th?
Sure. So I guess I kind of wanted to start just thinking about what I think I'll be doing for the next little while at least, which is doing QCD calculations. And I think there's a whole range of things where those calculations will get better and better, and we'll be able to make standard model predictions for many more complicated things than we can do now. I don't really want to go into the details of those things, but at some level, those calculations are going to become routine and therefore essentially not interesting to a theoretical physicist. They're going to be something that, okay, eventually mathematical will have a function that is QCD, and you can get the answer to your matrix element you need for your experiment. But I think this is really made me think a little bit about what the role of computation is in theoretical physics, because that clearly is not just providing numbers is not where we're trying to get it. It's really how do we use computers to help us provide insight into the theories we're trying to test and the theories that we're trying to the models we're trying to come up with for nature. And so I think that role has changed over time, and I think it will change even more in the next 25 years. So I mean, if I think about people in the CTP using computers, well, I mean, there are people like me where computers are a really big part of what I do, and then there are people like Jesse and Tracy where computing is a substantial part, but it's certainly not at the level that I'm using them. And then there are people like Waddy, who I've just learned is interested in using machine learning on computers to understand the landscape of string vector. Right? I mean, there's a huge range of things that people are doing now.
But is it still theory?
It's theory when the goal is to do more than just understand one particular aspect of it, right? So in the context of QCD, I think that the real, in the future at least, the kind of real theoretical drive will be not just to understand QCD of nature, but to understand strongly interacting theories more generally. And that is clearly a theoretical aspect. Computing itself is changing a lot. Even classical computing is changing hugely. Of course, Aaron will tell us and be able to calculate everything for us using quantum computers in the next 25 years, won't you, Aaron? Right?
So was that a segue? Do we do a cut?
It could be.
Oh, sorry, go. Aram?
Well, I do hope that in 25 years, quantum computers will be part of a, partly in the physics department, partly in the computer science department, partly in the math department, but also partly in the IT services part of the university. This will be one of the part of the infrastructure that we use to do problems in lattice QCD, in biochemistry, number theory. So I do hope that's part of it. And I do think also the way we think about it will also change. Right now we think about quantum algorithms mathematically, and I think it'll be more like biology and less like math in the sense that there will be kind of empirical regularities, but our understanding of them will fall short of theorems, which might be a little upsetting, but I think if you look at how classical computers are working, machine learning today is sometimes compared to alchemy in that there's sort of systematic approaches that people have, but not an overall theory, and some useful things you can do with it, but no periodic table. And I think that with quantum computers, there'll be the situation where our theorems will advance, and we'll be able to understand more and more provable algorithms, but what we can do will actually go far beyond that. And so we'll always be doing more than we can prove. So in this sense, even as we do more, we'll feel more confused. I think that'll be part of the future of quantum computing.
Sorry.
Yeah.
So I mean, one thing that's maybe surprising, despite how friendly we looked on the movies, is that actually, for example, I've never written a paper with any of my colleagues. We have many conversations in the lunchroom. But in thinking about who would I actually write a paper with first, it may be with you, Aram. Because we just are putting a grant application together. So I guess it better be with you, Aram,
right?
for deliverables. But do you imagine that either you or your students as a resource to explore other physics areas as a tool to be used, for example, in particle physics? How do you think that your role would be in that role?
Well, I think that, for a particular project, I guess we'll look at some uses for machine learning, quantum computers for machine learning problems. And then I think more generally, so I think, and I think in general, quantum computers will be, I guess you heard this morning, Andrew, I don't know where Andrew Childs is, but he gave this nice talk about using a quantum computer for quantum simulation. And there, the situations we've kind of where people have worked out the most concretely are molecules and condensed matter systems, but definitely nuclei and quarks and so on are part of that, of what we'll use it for. But then also, yeah, we'll use quantum computers for machine learning, and then hopefully also use quantum information ideas to kind of inform the way we think about some of these theoretical models.
Right.
Like
I mean, I see you dragging me into your world. I mean, am I going to be able to drag you into my world, or I'm just going to be sliding towards your end of the table?
Well, one more speculative way that you might drag me into your world is quantum computers we often think of as taking in classical inputs. But there's some cases where they can take in quantum inputs. So actually, we have Paula Capolera, I don't know if she's here, but she's in the nuclear science and engineering, is using nitrogen vacancy centers in diamond and our control of the spins of that to get much better magnetic field sensors. And there are ways of viewing that as sort of taking in quantum input instead of classical one. And so this is pretty speculative, but if a particle collider's output could be recorded in a quantum way, this is, I don't know, maybe this is 50 years out, not 25, then it could be analyzed by a quantum computer more efficiently than the way classical computers analyze it. So that would definitely drag quantum computing people like me into thinking about what's happening at the LHC.
So we just need those quantum sensors.
Right.
Quantum trigger.
Right.
A quantum trigger, yes.
Yeah.
Oh, so we don't know whether or not that Higgs boson event was actually stored to tape. Yeah. Tracy or Daniel, one of you want to weigh in? CTP at 75?
Well, okay.
Sure, you go for it.
Well, I think that, well, maybe first to say something about what we were just discussing. So one of the things which I think is definitely going to be very exciting and even still in 25 years and beyond is that I hope at least we'll actually have quantum computers that we can use to do many-body simulation. And I want to emphasize this. So if you read the popular press, you'll get the idea maybe that quantum computers have something to do with security or factoring or speeding up a search by a factor of a square root. Okay, this is not what quantum computers are for. This is what computer scientists think quantum computers are for, but they're wrong. Quantum computers are for doing physics. And this is great for all of us, right? And Feynman knew that, right? If you look at the quote from Feynman that Andrew had in his talk, Feynman wasn't talking about factoring numbers. He was talking about simulating quantum systems. And that's where the real immediate exponential speedup is. That's the thing where, with 50, 100 qubits, you can already be doing something interesting. You don't need 10,000 qubits. And so, I think there will be a phase transition in the physics of many-body systems, which will be somewhat similar to what happened in fluid mechanics maybe 50 years ago, where fluid mechanics in 1900 was a sort of hard subject where nobody could really do anything. But then once we had digital computers and we could simulate things, then suddenly the whole field is totally changed. And you go to a conference, I've even been in my youth to conferences on fluid mechanics, and every single talk is numerical. You just wouldn't even consider not having a numerical talk in a fluid mechanics conference. And whole new range of phenomena which were never seen before are just discovered numerically. And I think once we have quantum computers, that's what many-body physics is going to be like. We'll finally be freed from the chains of perturbation theory.
The chains of perturbation theory.
Yeah. So I'm excited about that. I think that's already enough to keep us all busy. Even if the LHC doesn't discover anything, and it's all pulsars, and of course I'm on my own also having I'm also having fun, of course, thinking about quantum gravity, and I think in a 25-year timescale, certainly I think the quantum mechanics of black holes I think we probably will understand. I think the quantum simulators will help. Already that connection is just getting closer and closer every day. Hopefully eventually we'll be working on cosmology. That's the, eventually we have to deal with the fact that the cosmological constant is positive. It's embarrassing, but.
Tracy, you want to?
Yeah, well, I don't know if we're going to get the cosmological constant in 25 years, but I'm going to say the obligatory thing and say that I hope we have the dark matter, because that seems like an easier problem. But yeah, so ideally either we'd talk about the discovery of dark matter or have it be like not something you talk about because it was 20 years in the past, 25 years from now. In terms of new data that will be coming in my area, I'm really excited about new data coming in both from near-field cosmology and from mapping out the stellar distribution in our general neighborhood. Surveys like, well, Gaia has already started releasing data. Their second data release is like in April, so that's not a 25-year timescale. That's a 1-year timescale. But surveys like LSST are going to really map out the volume of space around us much better. We'll have a better handle on well, from a dark matter perspective, we'll have a better handle on where the dark matter is in 25 years. I hope we'd have a much better understanding of what are the smallest dark matter structures that actually have stars in them. I hope we'd understand better if dark matter has its own interactions, as Lisa Randall talked about, then what would the observable quantities be of that? And we'll have a much better set of either constraints on that or a discovery of that kind of physics. Hope we'll have, but basically a better understanding of how dark matter behaves both in the presence of baryons or if you're looking at systems which have very few baryons in them. And I also think, as I said, that early universe cosmology has the promise to provide us with whole new windows onto fundamental physics. If this 21 centimeter observation from 2 weeks ago is right, then it's the first opening of a whole new observational window on the early cosmos. If it's wrong, then we'll still probably get that window, just maybe a few years down the track.
Tracy, I mean, some of these things, I mean, you're talking about things that are, sometimes in the nonlinear regime of trying to understand things where computation becomes essential, data analysis becomes essential.
Yeah, but and these are in many cases places where it's not a matter of like we have some beautiful theory, some beautiful, elegant, linear theory, and it's just a matter of getting the data and seeing if it agrees with our beautiful, elegant, linear theory. Like, there's a lot of work to be done on the theory side, and maybe we can do some of that analytically, but developments we're probably going to be doing a lot of it numerically, and maybe we'll be simulating on these quantum computers these big interacting dark matter structures with multiple clusters colliding with each other. We see systems like this. The question of what they mean for us is really unclear at the moment. And I do think this is likely to be a general feature of the next 25 years, that we have a lot of data, and the question of what are the right questions to ask. First, how do you formulate the right questions, and how do you get the answers to those questions out of the data are going to be big and serious questions. And I think this will be only more true, not just more data is coming in, but at least in my field, there's also first a trend in the particle physics community to make more data open, and also a trend for theorists to work more closely with data, more closely with experiments, and even to get involved in designing new experiments, as Abracadabra, that Jesse has worked on. And I mean, okay, you could say that we're still these like extraordinariuses wanting to be ordinariuses as we dabble into data. But I mean, I think the push towards more public data is a really positive thing, but it's something that our field is really going to think about how we handle, how we make sure that people who actually took the data get proper credit. And maybe the line between experimentalist and theorist is going to blur a little bit as we go through that. But I think, theorists, at the moment, the reason why you want a theorist perspective on these things is often that we have there's this huge sea of data. It's not at all obvious what sort of questions you can answer with that data or how you would go about answering those questions. And coming at it from a theorist perspective can be very helpful.
So one of the things that hopefully we save some time for is to get questions from the audience. How much time do we have for the infinite? No boundary? 15 minutes? Well, so if people want to start thinking about questions, I did want to actually probe our session chair a little bit on this, because one aspect that's actually really important in the CTP that you see in the architecture is the literal bridge to condensed matter theory. And I don't know, Hong, if you want to say anything about 25 years from now, and I am talking to you, Hong, yes.
Yeah, I think actually I'm old enough to know not to make any predictions. Unless it's supported by your own calculations.
That's why you make us do it?
That's right. That's why we ask young people to do it. Yeah, but listening to the discussion reminded me a story. So a few years ago, I was at a conference in Kyoto. So yeah, it was a typical conference, say, during the last 10 years, which the organizers brought, say, condensed matter people, quantum information people, string theory people, quantum field theory people together, just to talk about stuff of interest to each other. And then during the banquet dinner, so where people were waiting to take bites on the huge, like maybe 4 or 5 feet long fish, and the organizers stopped people, say, let's wait, and let's ask John Cardy to say a few words. John Cardy is of the most senior physicists there. And he stood up and he said, actually, I don't have much to say, but I want to say a few words to the young students and the postdocs in this conference. He said, I think you should know how lucky you are right now. He said, in my long career of theoretical physics, something like this has never happened before. Somehow, like condensed matter people, they're pouring through general relativity and black holes, and the string theory people are looking at the quantum error correction code. Yeah, of course, this last part I couldn't remember very well. I made it up because of the Daniel is here. Anyway, so he said something similar, and of course, I didn't remember his exact original words. Anyway, he was emphasized, even though I was not a young student in the audience, even though I didn't have the, say, the long perspective of a career like him, but his word resonated with me, greatly. So I do feel we are actually living in a special time in theoretical physics. And right now, we are seeing a theoretical structure, somehow a very complicated quantum many-body system with lots of degrees of freedom strongly interacting with each other. But somehow, against all our intuitions, they have very, very simple descriptions in terms of gravity. And why, in terms of classical gravity or quantum gravity, and why that's the case, we don't quite understand. And somehow, when we just see a rough structure, bits here and bits there, say, encompass essence of quantum gravity, encompass many essence of quantum many-body physics, etc. So right now we see some rough bits of such a structure. So hopefully in 25 years we will understand this structure much better. Right now, even though we have only seen bits of it, lots of insight has already been gained, both to condensed matter physics, or to QCD, or to string theory, to black holes, etc. But so far there hasn't been any, say, home runs yet. Say, like we haven't solved the QCD using this new thinking, even though there are some insights. We haven't solved the high TC superconductivity or turbulence, or we haven't completely solved the mystery of the black holes. But hopefully in 25 years, we will see maybe a rough contour of this grand structure, which includes quantum gravity, quantum many-body system, with entanglement play a key role, etc. And yeah.
You did a very good job of not making a prediction there.
I have a prediction, actually, for condensed matter, which is probably less grounded in reality. But if we're talking 25 years, I think plausible, which is that one thing we saw partly motivated by quantum computing is in a quantum computer, you can engineer systems that could look pretty wacky. And some of these systems, as you scale them up, do not look like field theories. And I was thinking about that during Lisa Randall's talk about how the WIMPs are what are easy to look for, but maybe we should look at other things. And the quantum field theories have a lot of desirable features of them, but what if there are things that are not quantum field theories that come from local models with local interactions? And I think quantum information-inspired thinking may help us make sense of these models And we may find that we've been looking under the street lamp for our keys, and there are a lot of other interesting things out there once we start going beyond field theories.
Yeah, well, one other thing I was thinking, so this is a slightly different direction, but I think also important. So, I was looking at, during David Kaiser's talk, I don't know, he's still around here, so there he is, yeah. So he's showing all these pictures, and of CTP 50 years ago, it was all these white dudes.
If you look at the current CTP junior faculty,
exactly.
in fact,
So, right. So I was going to say, yeah. So right. If you look at this table, it's looking a little bit better.
But it would be nice if in 25
that's
years the group of 5 people who are sitting here looked more like the population cohort in
That's
the US
right.
or in the
Yeah,
world.
yeah. And actually, Chanda was reminding me during the break. I mean, CTP does have some history with this. I mean, I think 2 of the first African American physics PhDs in the United States, Jim Gates and Shirley Jackson, are from CTP. So there's some tradition there, and I feel, so that's something I hope about CTP 25 is it'll look a little bit less like David's slides.
By the way, actually, I want to get back at Jesse. And so what do you think?
What do I think? Right. So of course, I had to prepare the question, right? So there's 2 things. In Henrietta's talk, it was like one of these talks that warms my heart because I feel, as much as I care about dark matter and particle physics, like at some core level, I'm an effective field theorist. And seeing from the bottom up, being able to just determine from the degrees of freedom what all the interactions are, just deeply satisfying and gives rise to a sense of almost like smugness, being an effective field theorist. And I suspect that this smugness will be wiped off my face in 25 years. And it may be even sooner than that. I mean, lunchtime conversations, for example, Daniel, about the difference between discrete and gauged, gauged and global discrete symmetries. This is something that an effective field theorist just doesn't care about because the predictions, at least in the context of perturbation theory, become the same. But the idea that some echo of quantum gravity will then start to influence the types of effective field theories that I think about. That's something that, well, in some sense, I hope changes in the next 25 years. And then there's another thing where Bullock is. He was mentioning, people in the LNS taking some of the ideas from my group and running with them. And it's an interesting question: who's working for whom in that relationship? That increasingly I see myself using data. And then I see my students going even further. So just to call out 2 of my students who showed up here. So Lena Nesib is using astrophysical data to try to map out dark matter. And that's a level of data analysis that maybe I'm the dinosaur for not wanting to jump right in and do even more of that data analysis. Or if I look at my student, Yoni Khan, who's involved in this abracadabra proposal. Okay, so I can call myself a dabbler and I get to stand next to Lindley Winslow's refrigerator. But Yoni is someone who's taking even that ideas one step further and really thinking about condensed matter experiment and what type of condensed matter systems can you use for dark matter detection. And in some sense, should I go even further in this realm of interfacing theory with experiments such that when I call myself a particle theorist, that I'm kind of wrong on both fronts, that I'm neither a particle person because I can talk to my colleagues here and I might get dragged into the nuclear world or into the astro world or into the quantum information world. And then also, in terms of that designation theorist, I will always want to have my office in the CTP. I really love it. You're not going to move me anywhere. But that I may find myself visiting down the hall even more, getting even more enmeshed in that world. And maybe all of us are going to be pushed in that way because it seems like we're going into a very heavily data-rich, computation-rich future in the next 25 years, maybe. Let me say one other thing, just to guarantee that the opposite happens. So you say don't make predictions. So I predict that 25 years from now, we're going to be still arguing about the hierarchy problem, and that we will not have a solution to the hierarchy problem. And so now you can take that clip, and when I retire, you can show that, because hopefully that will guarantee the opposite is true. That we'll have a solution. Questions, comments from the audience? I see a lot of them. Let me point to one of my former students, Mobalaji. And there's microphones someplace. On the aisle.
Please come to the mic.
Hi.
So you guys talked about how your work as physicists might change in 25 years, but I'm a TA at Harvard, grad student there as well, and I've noticed that the students, they have a very good familiarity with linear algebra, but they know less about how to solve differential equations, and this is quite different from my own education here at MIT, and I think this is perhaps a function of the fact that we're moving into a more computational sort of science and engineering apparatus where linear algebra is more effective than just differential equations. So my question is, in 25 years, how do you think the training of theoretical physicists, both at the undergraduate and graduate level, would change or be different?
Well, I think that the quantum information approach can inform the way we teach quantum mechanics. And already there's some approaches that begin by building on your intuition from classical mechanics with a particle that has position, momentum, and then energy and angular momentum. And there's some approaches that start with the spin 1/2, which is mathematically easier, but has no classical analog. So the Feynman lectures are one example that take the spin 1/2 route. And it may be that in the future, I think there are advantages to both approaches, but it maybe depends on the student's background. If students come in more comfortable with linear algebra, maybe at some point high schools will catch up with the developments of the 1960s and start teaching programming. Then at some point they may be comfortable with bits. Then it may be that that's an appealing approach to teaching quantum mechanics. That's one change that I anticipate may happen.
So one of my biggest regrets from my physics undergraduate time is that I never really took any programming classes. I did Mathematica, but I never learned an adult programming language. And I feel like already that should be a requirement of physics majors.
I mean, likewise, I think I had this third of a semester on computational physics, which was entirely about MATLAB, and I didn't learn how to code until I got to grad school. And actually, the context of that was that I said to my advisor, I have a strong background in math, and I know how to do analytical calculations, but I don't really know how to code, so I would prefer not to do projects that involve a lot of numerical work. And my advisor was like, oh, that's pretty limiting. And I was like, so he suggested to me a bunch of projects, and I was like, oh, okay, this one, I think it has small parameters in it. I can do a perturbative expansion. I was still happy in my chains of perturbation theory, you see, at this point. And my advisor was, oh, yes, sounds like a good idea. So then I went away, and I came back a week later and said, none of these parameters are small, and none of them are very large, so I can't expand in the inverses either. Like, every parameter in this problem is between 0.5 and 2, so I don't know how to do a perturbative expansion. And my advisor went, yeah. And I went, so maybe I need to do it numerically. And my advisor was like, yeah. And I had a very good advisor. And so eventually I asked him to teach me how to do it numerically. And that was how I learned to code. And already, for me, it's just been an enormously valuable tool that's opening up a lot of opportunities. But so, yeah, I mean, I think all our students should learn it. At the same time, I do think you still need to know how differential equations work, because occasionally, I feel fairly confident this will still not be true in 25 years. There will not be an algorithm for absolutely everything you want to do. And they will mostly not be targeted at people doing cutting edge research. So occasionally you will have to think about your own algorithms, and at that point, it helps to know about differential equations.
Hello, Ulrich Becker. I have a wish on the next generation. After my generation spent endless time on getting the standard model right, I wish that somebody thinks about why the 12 elementary masses are the way they are. And that's my wish to be resolved in the next 25 years, if you can.
We'll try.
So I'd like to turn the question on its head for a moment and ask, which questions in theoretical physics do you think there will be little progress on in the next 25 years? And just to capture the low-hanging fruit, I think we'll take the cosmological constant off the table.
mean, one of the example that I mentioned about the hierarchy problem, this is a case where, of course, one hopes that some UV physics can actually explain the hierarchies of scales that you see to generate large infrared scales. But I'm not so optimistic about that, and nor do I know that it's necessarily relevant, and that I'm influenced by thinking of that there may be things beyond our cosmological horizon that we need to think about in terms of understanding what we see. So that's an example of something where, yeah, maybe there's not going to be progress, which was part of the reason why it's easier to chase things directly like dark matter, something we have observational evidence independent of theoretical motivations.
We have a lot of evidence about flavor, but we don't know what to do with it.
Well, right, flavor is...
Flavor is a good one.
Yeah.
Is there one more question?
yeah, Frank, you want to...
I want to ask, when do you think our best students will be AIs? And then when do you think our best colleagues will be AIs?
You might have noticed that at least three of us mentioned machine learning as something that we're doing a lot of and thinking a lot about. And I think it's a very interesting question how AI will play a role in what we do, and when it will take over what we do. I mean, the things you see AI doing now are pretty impressive, and I mean, something like playing Go is not, playing Go and pattern recognition are things that are part of theoretical physics, right? I mean, those linkages are what we do.
The other thing that's really impressive to me about the AIs I've seen is frequently they find solutions that are just not the way a human would approach the problem at all. There are some crazy examples of AI, well, actually in some cases exploiting bugs in the code, like AI locomotion and stuff, where you end up with a solution which it works well, it's really efficient, and you look at that and you're like it's not a small perturbation of some previous the solutions that your intuition tells you is right. And so it's really hard to think of it as a human being. Whereas, so I mean, it's exciting to me that you might be able to find those solutions which are just in very different parts of the solution space than the things we normally think about. But yes, I mean, this may mean that the robots take over. But it's exciting to me from a scientific perspective.
Let me push back on this a little bit. I lived in Silicon Valley for a while, and I got fed up with the hype. So,
I'm speaking from a very uninformed perspective. I've just seen the AIs doing cool things. So.
Yeah, they're going to take over other departments first.
Yeah, okay. That I believe.
I mean, AIs are good at solving problems where the rules are clear in advance. And the thing that's great about theoretical physics is the rules are not clear in advance. And that doesn't mean that eventually we're not going to have AIs who can deal with that too. But I think that the AIs we see today, there's not even close to that kind of thing. So,
they're good at solving well-posed problems in unconventional ways.
You tell it, here's a number, and you want to maximize this number, and here are the operations you're allowed to do, and that's what it's good at. Yeah. I don't know. I'm not worried about my job, at least not for that reason.
So let's thank our panelists. And let me here be very brief, because we've had a long and for me, outstanding day. I want to do another round of applause in a second, in which we will thank all of the speakers, all of the session chairs, some of whom were just drawn into the panel, and one person who you have not seen because he's been making everything happen elsewhere, and that's Scott Morley. When you see Scott Morley at the dinner, those of you who are coming to join us for dinner, the bar opens in 5 minutes. It's over in the Sandberg Center, which is more than a 5-minute walk. So by the time you get there will be beverages. So those of you who are coming for dinner, please join us. And to everyone, thank you for coming. It's been great having such a great gathering of the CTP, the first 50 years and the next, I would say, 50 years. Thank you very much, everybody.